Okay, we're going to redo this problem together. So, key things we want to add in here. Independent variable is always going to be on the left side of our table. More times than not, it's going to be the first thing that we record. Dependent variable is going to be on the right side of our table. So, key thing here, we want to look at what our table is representing. It has wingspan and mass of birds. So, right off the bat, we know that these should be the labels of the axis on our graph. So we can cross off any graph that doesn't have that. So let's take a look. This one has wingspan, mass. So we know that that's good for right now. This next one over here, bird number and cm or kg. Neither one of these things says bird number, so we know we can cross that off. This one down here, bird numbers again, and we don't even have a label over here. We know we can cross that off. So we're down to these two. So key things here, there's two ways we can figure this out. One is, if we remember that independent variable is always on the left side of the table, we know that wingspans are independent variable. Independent variable is always on the x-axis. This one is the only one that labels it on the x-axis. But if you forget that, we can take a look at our numbers. Wingspan, all of these numbers are in the 200s. So let's take a look at this graph. Wingspan, all of these numbers are in the 200s. This wingspan, the numbers go from 0 to 8. These are not the correct numbers for our graph, so this is our answer. Okay, this one. Carl collected some pill bugs. He put them in a cardboard box in his garden with a hole on one side. He drew these diagrams of the pill bugs remaining in the box at the time shown. Carl sounds kind of like a creep. So at these different times, we have 325, 334, 348. So he started timing. All of our times are in the threes. So right off the bat, which ones can we get rid of? This time goes from 0 to 70. He did not watch these bugs for 70 minutes, so we can get rid of that one. And we can get rid of that one. He did not watch the bugs for 70 minutes. So we're down to these two. What time did Carl start watching the bugs? Let's take a look. 3:25. Which one of our graphs starts at the correct time? This one starts at 0. This one starts at 3:25. Our correct answer is this one. Okay, go ahead and try that next one on your own. I think it's dealing with increasing, decreasing. All right, and conclusions. Go ahead and write these notes down. We already know independent variable is always on the x-axis, dependence on the y. We definitely know that we need to look for increasing, decreasing. And our key thing here is in pink. Compare the data to the hypothesis to determine whether or not the experiment worked. Our hypothesis is not always going to be right, and that's okay, but we need to compare our data to prove it right or wrong. All right. So some students were studying different parts of the water cycle. They used sponges to model water in soil. They cut out 4 identical pieces of sponge, added water, and put each one in front of a fan. The table shows the results of their investigation. Which conclusion is most valid? So key things here, we're working with a fan, and we've already wet the sponges. So what can we get rid of? A, precipitation is more likely when wind speeds are low. If we remember what precipitation is, that means like rain, snow, water forming. Water is not forming here. All we're doing is putting a fan on the water. So we know that's not right. The higher the wind speed, the faster the water will condense. Condense is the formation of liquid water. We are not forming water here. We can get rid of B. C, wind contributes less than sunlight to the water cycle. So we don't even have anything mentioning sunlight in our data, so we can get rid of C. D, the rate of evaporation from soil increases with the speed of wind. So water evaporating, it goes to the gas form. So we're going to be losing water with the speed of wind. We've already narrowed down that it's not A, B, or C, but let's figure out why it's D. So as wind speed increases, we are going to look at how much water is lost. Is the water amount decreasing? Yes, water is being lost. So it's D. All right, what about this one? Duckweed is a small aquatic plant. Students did an experiment in which they grew duckweed in petri dishes. Then they counted the duckweed every 2 weeks to determine the growth rate. They concluded that duckweed encountered limiting factors in this environment. If we forgot what this meant, we need to redefine it. This is from evolution. Limiting factors stop a population from growing anymore. They completely stop it. They limit it, so it's not going to keep increasing. So which data supports this? Where does our population stop growing? A, after a week, the population did not grow above 250. So after about 7 days, our population did not grow above 250. Is that true? Well, we see 100% that is true. After 7 days, we have 250 up here. Our red line, our population never goes above that. I don't really know what that was. Okay. So, evaluating models, theories, and designs. Go ahead, write these notes down. These are tips for how to answer these questions. More trials or more times you're doing something shows that you can get the same results over and over again. Someone else could do it and get the same results. If data does not support the hypothesis, it doesn't mean that it's a bad experiment. It just means that we need to repeat it. Larger sample size or number of groups equals more data and more valid. Valid is good. Experiment is invalid or not good if the conclusion does not support the data. If the conclusion does not support our data or doesn't include our data, then it's not a valid experiment. Adding control groups always make the experiment better. Adding that group that doesn't get the independent variable will always make it better. Okay, a scientist examines the amount of time it takes cells to complete the cell cycle. At the end of the experiment, he checks over his data. The data is not what he expected. Which of the following actions would help him verify his data? If the data is not what we expected, we are going to repeat our experiment. It's like doubling back and checking our work. All right, a science researcher is reviewing another scientist's experiment and conclusion. The reviewer would most likely consider the experiment invalid. Invalid is bad. If A, the sample size produced a lot of data. That's good, so we know that that's not our right answer. B, others are able to duplicate the results. We want that to happen, so that's not our right answer. C, contains conclusions not explained by the evidence. If we have conclusions that are not supported by the evidence, that is bad. Not good. D, the hypothesis wasn't supported by the data. Our hypothesis, it's okay if we prove it wrong. If we prove it wrong, we're just going to run more tests. But the only thing that would make our experiment really bad is if we have a conclusion that is not supported by evidence. If we don't have evidence to back it up, it's not a good experiment. All right. You have just completed the inquiry. So you